Hello and welcome to the first video on my channel. Today we're going to be reviewing triple integrals in spherical coordinates, and we're going to be solving three different volume problems that have customizable bounds. But first off, we can get into what spherical coordinates exactly are, and we can define that as the Greek letter rho, Greek letter phi, and Greek letter theta. And these are going to be very helpful in solving some forms of volumes, because if you were to try to do them in Cartesian coordinates, it'd be so complex, so annoying. If we're able to make these simple translations, it makes it so much easier, and it takes it to, um, you can also get it to a lower dimensional level, which I'll describe in a second. But we're going to start off here with the basic translations. So x is going to be rho sine of phi cosine of theta, and y is going to be rho cosine of phi of sine of theta. Double check here, because this, yep, that's, oh, we're gonna swap these two right, or this one right here. This video is also an assessment of my personal knowledge for my knowledge gain, so just keep that in mind. So this is how you'll translate each coordinate or variable that from Cartesian to spherical. And then also there's a rule where, and we derive this from the spherical equation of x squared plus y squared plus z squared equals rho squared. And this is the same as x squared plus y squared plus z squared equals r squared. And if we are to dive into what exactly spherical coordinates look like on an xy plane, we can see why this is very understandable and it's very visual. So let's say we had our line here, rho. Okay, so rho is going to be basically the radius in this case, as you can tell. And we're going to have our phi right here. So this is going to be the distance from the z-axis, from here to here to here to here, and it's going to continue to change, and it's going to be that measurement from the z-axis of rho. So then we can also go here, because we're imagining that it is coming towards us a bit, this vector that we're looking at for rho, the length rho, and we can see that theta is going to be the distance from the z. So now you can kind of picture how we derive these coordinates from our Cartesian, and this is going to be helpful for finding the bounds of each one, because we're going to have to really know on a conceptual basic level of how these spherical coordinates relate to the Cartesian coordinates. And this picture right here is basically going to be your guide. So another one to define real quick, because we analyzing this integral right here, we can define this as a density equation, and then we can define this as the it's like kind of the volume constant, and you have to translate that into spherical. So dv is always going to equal this, which you just have to remember is rho squared sine of phi, and it's going to be d rho d phi d theta. And you're going to be using this equation here for basically every application. So this is going to be a good thing to remember, as well as all of them. They're all very important here that we've all listed. So we're going to be referring back to these multiple times when we're solving these problems. So we basically lay out everything that we need to go ahead and solve number one here. So we'll go ahead and do that now. And what we have is a ball B centered at the origin with radius 5. So right off the bat, if we were thinking about radius, we can think of rho. They're interchangeable, so we can say that rho ranges from 0 to 5 because it was centered at the origin. And we're going to be writing in blue here. So we have one of our bounds, but we need to hit all three of them. So next we have phi, and we can figure out phi is going to be, it can max, phi is a value that can max at theta. So we're going to put theta, or not theta, pi. This value can kind of max out at pi, and then it can be like pi over 2 if it was restricted there. There's no restrictions. It's going to be a full sphere. So if you imagine a sphere on this picture, it's going to be unrestricted for phi. So that's what we're going to do there. You really have to understand how these coordinates affect the Cartesian to be able to find your bounds. And theta is going to be all the way to 2 pi because we have a sphere. So if you were to do a full circle on this xy plane, you'd be covering a full 2 pi. And because we're imagining an entire ball, they say, which means a completed sphere. So that's how we're able to find our three coordinates, and that is arguably one of the most complicating steps because if we're solving these problems, we're assuming you have basic integration down and triple integration. So it's more about just knowing how the spherical coordinates relate to Cartesian. So what we're going to do now is once we have our bounds, we can basically start integrating or setting up our integral. The way we're going to set it up is theta, phi, and rho. So for theta, we said we had 2 pi to 0, and then we had pi to 0 and 5 to 0. Now inside we have our density equation. Now our density equation we're going to have to translate. We can't have the Cartesian in the spherical integral. So right off the bat I can see that this right here is going to translate to this. So we're simply going to replace it with rho squared inside. And obviously that's squared as well. Now we have to put in our dv because we have our dv at the end there, and that is going to be defined as rho squared sine of phi, and then d rho d phi d theta. Right, so now we can simplify this out a bit, and you can match theta, theta, phi, phi. I mean, this is basic triple integral stuff. I'm hoping that when you're at this level, you already have a lot of that knowledge. So simply simplifying our integral, we have rho to the fourth, or wait, we have rho to the fourth, and then, so we have rho to the sixth of sine phi, and then d rho d phi d theta. Now, what we can do from here is, since there's not many restrictions on this problem as a whole, we're going to be able to do a thing where we can separate integrals. And I'll introduce this concept here, where this is what's nice about spherical coordinates, especially, is if you have an integral of rho, phi, and theta, d rho, d phi, d theta. Well, actually, you don't need to exactly have these here, but you can. What you can do is you can split it up in a way that you were unable to do before, which is like this. And then you can multiply the results of each one, and basically you just have to combine. So like if there was some phis or some rhos here, you would just literally subdivide them into each separate integral. And that makes it very easy. It's a way that you could never divide them before, and it's going to make evaluating this very easy. So taking that concept, I'm going to have my theta integral here from 2 pi to 0. And we have for thetas, it's only d theta, so we can solve for that. Then we have pi and 0 for phi, which we only have a sine of phi, d phi. Then the last one for rho, we have 5 to 0 of rho to the 6th. So at this point, what I like to do is label them number 1, number 2, number 3, and we can go ahead and evaluate each one individually. Now, for the integral there, for d theta, you can obviously see that it's just going to evaluate to 2 pi, so that's a very quick and easy one. Number 2, we can evaluate the integral from pi to 0 of sine phi d phi, and this is going to equal cosine of phi. Well, that would be the derivative. Actually, we need negative cosine of phi from pi to 0, which equals negative cosine of pi minus negative cosine of 0, which would evaluate into negative cosine of pi is, well, cosine of pi is going to be -1, which is going to make that 1, and then plus cosine of 0. Cosine of 0 is going to be 1, so that means we have 2 right there. Because, right, cosine of pi, negative, yeah. Right, so far we have 2 pi and 2, and then for number 3 we can evaluate 5, 0 of root of the 6 d rho, which is going to be root of the 7th over 7 from 5 to 0, which is 5 to the 7th over 7 minus 0. And we can evaluate that as, let me use my calculator real quick, 5 to the 7. Alright, so it's going to be 7, 8, 1, 2, 5 over 7. Alright, so then we can multiply that by 2. 156,250 over 7. We're also going to need to multiply that again by 2 for the pi, which we can evaluate into 3,125,500 over 7 pi. And that's going to be our solution, as I've found from this value. And with that, we'll continue on to the next one, where we need to find, okay, so we're given the bounds for rho, and we're given the bounds for phi, so we can automatically write out rho is going to be from 2 to 4, and phi is going to be from 0 to pi over 3, because if you imagine a cone is going to look something like this, right? And if you're imagining the distance between, from the, see, this distance is going to be your phi. So if they say that distance is going to be pi over 3, we can assume that it's going to go from 0 to pi over 3, because it'll start at 0 and get bigger and bigger all the way to pi over 3. Or that's just pi, not bigger to pi over 3, but that pi over 3 is going to be the value to describe that angle. So theta is going to then be from 0 to 2 pi, because in a cone we are looking at the entire circle on the xy plane. We're not restricting to any octants or any regions. So now that we have our bounds, we have quite the simple integration here of 2 pi to 0, and we have theta, phi, and rho. And the next one we have 0 to pi over 3, 0, and then rho is going to be, as we said, from 4 to 2. So now with this information, we can translate our x, y, z, and we're going to put in the translations for each one. So for x, we had rho sine of phi cosine theta, and for y, we had rho cosine of, or sine of phi of sine of theta, sine of phi of sine of theta, and then we also had rho of sine of phi. I'm correct. Nope, cosine phi. And this is for translating a simple xyz. We simply put in those. And now we're going to add in our dv, which can be rho squared sine phi d rho d phi d theta. Now we can combine like terms, which is going to give us our triple integral here of rho. Looks like we have 5 rho to the 5th. We have sine cubed of phi there, and then we got these. Now we have sine, okay, so we have 1 cosine phi. Now we're done with the phis, and then we have a sine of theta and cosine theta. And then we have our d rho d phi d theta. So now from this, what we're going to do is we're going to separate the integrals, and we're going to do the theta first, so 2 pi and 0. It's going to give us sine of theta cosine of theta d theta, and then we have the integral from pi over 3 to 0 of, and this is going to be our phis. We're going to have sine cubed of phi cosine phi d phi, and then you're going to have 4 over 2 of phi to the 5th, or rho to the 5th d5. So we're going to label these number 1, number 2, and number 3, and we're going to evaluate all 3 of these. So we're going to make a little box here. Number 1, this is going to be, so 2 pi to 0 of sine of theta cosine theta d theta. Now this could be trig substitution. I like to call it trigonometric substitution, but I like to call it trig sum. And you can also do u sub here. That's what I'm going to attempt to do here with u equals sine of theta, because du is going to equal cosine of theta, and d theta, so that means that du over cosine theta equals d theta. Right, so then integrating with that, we have u, and then we have du right there from our 2 pi to 0, and then that's going to equal u squared over 2 from 2 pi to 0, 2 pi squared over 2, that's just going to equal pi squared. Wait, let's think about that a little more deeply. Let's make sure we get this algebra right. It's 2 pi squared over 2, which is going to equal 4 pi squared over 2, 2 pi squared. That's going to be for number 1. Now we can go over here and we're going to solve for number 2. Number 2, which we said was from pi over 3 to 0 of sine cubed phi to cosine phi d phi. And what we have to do from here is we could do another u sub, but I think trig sub is going to be the best method here. So this one is solvable through another u sub. U is going to equal sine of theta, which makes du equal to cosine theta d theta, making, as we said before, d theta equals du over cosine theta. Now, so we have a u cubed, and basically what we're going to do is we're going to have here of u cubed d theta, because our cosine gets divided out, which is going to equal, well, I mean, say du here actually. And obviously that's not theta, that's all phis here. My mistake. But that's going to be u to the fourth over 4 pi over 3 to 0. So pi over 3 to the fourth over 4, well, not actually that. What we have to do is put back in the we have to find these bounds in our u world, so sine of pi over 3 and sine of 0 is going to equal 0, and sine of pi over 3, if you think about the unit circle, is going to be root 3 over 2. So we're going to have basically root 3 over 2 to the fourth over 4 minus 0, and that is going to simplify to 3 squared. Um, hmm. I mean, yeah, we can distribute that, but I don't get where the fourth goes from. 9 over 16. We have our 1/4 here. I don't know why. So it's actually 9 over 64. It's going to be our solution for number 2. Number 3, we're going to solve here as the integral from 4 to 2 of rho to the 5th, 4 to rho to the 5th d rho, which is going to be obviously just rho to the 6th. This is basic integration. 4 to the 6 over 6 minus 2 to the 6 over 6. We can use our calculator here to solve this. 4 to the 6 divided by 6. Okay, so what we have over here is 4096 over 6, and then we have 2 to the 6 divided by 6, so we have 64 over 6, so 4096 minus 64 is going to be 4032 over 6, which can be simplified to a whole number of 672. And then finally, combining all our values, we have 2 pi squared times 9 over 64 times 672. It's going to give our answer of 672 times 2 for the pi, so it's going to equal a total of 189 pi squared. It's going to be my solution for this problem. Now finally we're going to evaluate this last one, another ball, but we have a portion of the ball that lies in the first octant. So for this one, what we're going to do here is recognize that this can be set to rho squared, so we're just going to do a quick translation of xe rho squared, and then we have our rho squared sine phi d rho d phi d theta, And then for x, we can put in our x here, which is going to be rho sine of phi cosine theta. And through this, we're going to split this up into 3 separate integrals again, and then we'll find our bounds. Oh, let's find our bounds now. So rho is going to range from 0, well, let's see here, 0 to 1, because we have our radius of 1 right here. And then we have phi, which is going to be from, let's see here. If we have a portion of a ball that lies in the first octant, that would mean that you have positive, let's say this is again your x going here. So this is negative x, and this one's going to be negative y, negative z. So the first octant is going to be, I'll try and draw this here, but it's going to be flat on the xy plane here. And then it's also going to be flat like a wall here on this one. So now on our side of this image, because we have basically what you could see as a floor right here, and then we have a wall right here, anything within our region here is going to be the first octant. So we have our sphere here, and if we have our sphere, it's basically going to be a, with radius 1, it's going to be bounded to this kind of quarter of a sphere. So if you were looking at it from this another angle like this, you would have, as I drew in red right here, like this as your sphere, because it's bounded both ways. Right, so there you go. We've defined what the first octant was, and if you were to think about that in terms of phi, what we would have here is phi extending all the way down to the y-axis, which I'm going to define as pi. Now, if it were to go further than that, we would call that a full range, we would call that 2 pi. So we have 0 to pi here, and then we have theta from 0 to, well, actually no, I think this would be more of a conceptually pi over 2, and this would simply be a pi. And then if you were to do a full circle, okay, I understand, I see it now. So pi over 2, and then if you went to half, that'd be 2 pi. If you went here, that'd be 3 pi over 2. If you went all the way through, it'd be 2 pi. That makes sense. Not 2 pi there, that'd be pi. 3 pi over 2, 2 pi. Alright, so actually what we have here for phi is going to be pi over 2. Just solving for our bounds here. This is the most important part, because if you get this conceptually wrong, then you're going to have a wrong answer every single time. So you need to make sure that this method is perfect. And now for theta, we're going to be looking at, so this is kind of like our YZ plane. So we have Y and Z here. But if we look at it from now in X, Y perspective, like a top down, what we have here is a restriction. This is going to be our sphere. Looking at it from top down, as you can see in this image, that's what it looked like. And our theta, which is the distance between the x and the y, that's going to be another pi. I think that'd be a pi. but maybe a pi over 2. Unless I'm thinking of it wrong and the first octant is actually going to be defined as cut off. This is not part of the image, and we actually have not a quarter of a sphere, but an eighth of a sphere. So yeah, actually this is correct in my analysis of you'd have 1/8 of a sphere, which makes this image incorrect. And what we actually have here is this is what our sphere looks like. So if you're thinking about theta from y to x, it is actually going to be pi over 2, because then if you went to here, it'd be pi. If you went over here, it'd be 3 pi over 2. And then all the way around, obviously, it'd be 2 pi. So what we have here is another pi over 2 for our bounds. I'm glad we were able to get that right, clarify everything so that we can get the right answer here. So theta, pi over 2 to 0. And all of our thetas, we have cosine theta and a d theta. Then for our next integral, we have for phis, which we said phi was again pi over 2 to 0. We have sine, so we have 2 sine phis. Start crossing them out here. We got our theta, got our theta. Alright, and then after all that, all we have left is rho. Perfect. So we're going to do this. Rho we said was from 0 to 1. And we have rho cubed, e rho squared, d rho. I'm going to label these number 1, number 2, number 3. Alright, so we're going to shrink this down a little bit just for room's sake. But we have our 3 integrals here defined nicely and correctly because we made sure we got those bounds correct, corrected our errors. Number 1, we have cosine theta d theta from pi over 2 to 0 here, which is simply just going to equal the antiderivative of cosine is sine of theta, and then from pi over 2 to 0 is going to equal sine of pi over 2 is going to be 1, and then minus sine of 0 is going to be 0, so it's going to equal 1. So we have that one taken care of. Now we'll go over here and do number 2. Number 2 is going to be the integral of pi over 2 to 0 sine squared of phi d phi. And we're going to use a trig identity that says that sine squared of theta is going to equal 1 minus cosine 2 theta over 2. Obviously we've got past all the spherical. This is just normal integration, so if you're not interested in this, obviously we've covered the main topics of the video, excuse me. So we're gonna do the integral, we're gonna pull our half out, and we're gonna have 1 minus cosine of 2 phi. Now we're gonna split this integral into 2, so we're going to have half, and we're going to have 1 d phi, and then we're going to have minus integral of cosine 2 phi d theta, or d phi. And through this solution, we can find a, plug in pi over 2, we can simply do that for this one, and then cosine of 2, so that's going to be basically what we're saying here is sine of phi, obviously 2 phi, but it's going to be from pi over 2 to 0, which equals, which we can further define as sine of pi minus sine of 0. Sine of pi is going to be -1, so basically what we have here is -1 minus 0 half times pi over 2 minus -1, so it's going to be +1. And overall, I mean, we're just going to keep that for now, but that's 1, 2, and then we'll go ahead and do number 3 here. So number 3, what we have is from 1 to 0 of rho cubed e rho squared d rho. Alright, now, this one might be a little tricky, but we're going to do some u substitution here, and we're going to set u equal to rho squared, which that means d rho, or du, is equal to 2 rho d rho. D rho is equal to du over 2 rho. So that means that our integral is gonna have, we're gonna pull out the half from our 2 down here, and then we're gonna have u e to the u du as our integral. So, and our bounds are going to stay the same, because if you were to plug in 1 and 0 into this equation here, you're going to get the same values. So that's very nice. Now, how we can integrate this is we're going to have to do integration by parts. Because it is a bit complex of a setup there. So we're going to have w and dw, then we're going to have v and dv. And our formula states that the integral of w dv is equal to wv minus the integral of v dw. And so that means that our w is going to equal u in this case, which means dw equals du. And then v is going to equal, well, dv is going to equal e to the u, but that also means that v is going to equal, well, du. Maybe it's there, maybe it's not, I'm not sure, but I don't think it matters for our solution here. We're going to do that, and through this, we can now set up, even though we have a half overall that's multiplied by all of it, we're going to have u times e to the u minus the integral of e to the u du. So that's going to be half u e to the u minus e to the u. Now from this, we can pull out an e to the u, which would give us u minus 1. And bringing that up, we can solve this from, we can have our half out here, but we can solve e to the u minus 1 of 1 to 0. Can solve this real quick and then be done with this. E to the 1 of 0 minus e to the 0 negative 1 times negative 1. So e to the 1 times 0, that's going to be 0, and then minus e to the 0, which is 1, times negative 1 is negative 1. So we're going to have half as our answer for this integral. So now multiplying number 1, number 2, and number 3, we're going to have half times 1 times pi over 2 plus 1 over 2, which actually this solution is not correct. There is no plus 1. It is simply that, which would equal pi over 4 simply. That's why I thought that was incorrect. But this is going to simply equal pi over 8 as our final solution for this problem. That one was a bit complex because we had to use, obviously, integration by parts, use substitution, and a trig identity all together, which made it quite complex to integrate, but that was also nothing to do with spherical coordinates. So I think finding the bounds is really just the main concept here, and that's where a lot of it's either you're going to get the problem right or you're going to get the problem wrong. And that's why understanding the main concepts here is so important. And it's basically going to determine if you get the problem right or wrong. I can't confirm that all the answers you see here are correct, but this is a personal assessment for me. And it's also my first video to this channel, so I hope you enjoyed. I hope you got any benefits from it. I personally learned where I need to improve, and thanks for watching.